All right, so today we're going to finish the notes over Chapter 5, Section 3. Same format as yesterday. Electromagnetic radiation, when we talk about that, it is going to include all radiation from the electromagnetic spectrum. So that is radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. If you look on page 139 in your textbook, you will see that electromagnetic spectrum. So that's just this part right here. Right, this whole thing would be the electromagnetic spectrum. So electromagnetic radiation would include any form of electromagnetic radiation on this spectrum. So we see anything from radio waves to gamma rays. What scientists found out was that when light is passed through a prism, the different wavelengths are going to separate into a spectrum of colors. The different colors represent different frequencies of light and different amounts of energy. And so we can see that on page 140 in your textbook. So this is on page 140 in your textbook. On the left-hand side, you just have a regular light bulb. And when you take that light and you shine it through a prism, it's going to break up into a continuous band of colors. But when you take a helium lamp and you shine that light through a prism, it's going to break up into discrete color bands, which we also looked at yesterday in the notes. And each of these colors would have a specific frequency. And then we can use that frequency to calculate the amount of energy associated with that light. Now, the energy associated with that light is going to be the amount of energy it took the electron to move from the ground state to an excited state. And then that electron falls back down to the ground state, releasing that amount of energy in the form of light. So that's kind of the effect that you're seeing of what's happening inside the atom with the electrons. So here is the equation that we use to calculate energy when we have frequency. H is what we call Planck's constant. It's 6.626 times 10 to the negative 34th joules times seconds. That's the label for it. Energy would be measured in joules. Now, if you look on page 144 in your textbook, we can go through an example. So on page 144, sorry, I have to move some things out of the way here. On page 144, let's go ahead and just look at number 17. It says, calculate the energy of a quantum of radiant energy with a frequency of 5 times 10 to the 11th waves per second. That's what that label right there means. That's how it's read, waves per second. So what we do then is we use our equation from right here. We're solving for energy. So we're going to have energy equals, and then we're going to put the number in for Planck's constant. Times the frequency. And when we multiply those two numbers together, we should get the energy in joules. So 6.626 times 10 to the negative 34th times 5 times 10 to the 11th. And I get 3.13 times 10 to the negative 22nd. Seconds would have canceled out, and that is in joules, which is a label that makes sense because we were solving for energy. Now, when you type this into your calculator, you have to be very careful how you enter it. So let me just go through that one more time with my calculator. If you have a Texas Instrument, you can use this shortcut. If you don't, you're going to have to use parentheses if you're dividing. If you're multiplying, you don't necessarily have to use the parentheses. All right, so the shortcut is to do 6.626 and then find the EE button on the Texas Instrument calculator. So for mine, I have to use the second function and then press this button right here. EE means times 10, so I don't have to type that part in there. So 6.626 EE negative 22nd, and then times 5 EE 11. And then you press equals, and you get 3.13 times 10 to the negative 22nd joules. Now, if you don't have the EE button, then you can just do 6.626 and then times 10. Use your little caret symbol there to the negative 34th times.
Press the vote right if you're still in the building. Dial extension 2101. Press the vote right 2101, please.
Sorry about that. And then times, and I usually use parentheses if I'm not using the EE button, just to make sure things are being entered correctly. And you get the same answer, 3.31, I'm sorry, should be 31, not 13, times 10 to the negative 22nd. All right, so I hope that that helps with those calculations. On the back side here for the notes, kind of going back to our discussion about what's happening inside the atom. When atoms absorb energy, the electrons move to a higher energy level and then release the energy in the form of light when they return to the ground state. So when you look at the atomic emission spectrum that I showed you earlier, that's what you're seeing.
Mr. Palmer, dial extension 2101. Mr. Palmer, 2101, please.
This produces spectral lines that are characteristic of the element and make up the element's atomic emission spectrum. So these are very important points that you're going to want to know moving forward. And remember that when we're talking about the atomic emission spectrum that is formed, we are talking about this thing right here. This is the atomic emission spectrum. All right, so if you have any questions, just send me an email. Thank you.